Let's take a look at thermomechanics. So we can use Tm to represent it. T means thermal and M means mechanics. So in the past, you guys possibly have already heard some concepts about thermomechanics. You possibly have heard something called a thermal strain, thermal stress. Have you ever, so where did you heard thermal stress before? If you are pavement engineering, do you have thermal stress?
Yeah.
You have, right? Yeah. So we have some typical issues associated with thermal stress in pavement engineering. And they are the longitudinal cracks, right?
Yeah.
So if you guys have ever driven a car, on those low volume roads, county roads, that means if you get out of Holton, actually in Holton, they're low volume roads, right? They have relatively weak base and subgrade. You may observe something for some road sections. You may hear some noise. When you're driving the vehicle through, on the roads, you may hear some tapping noise, occurs over a certain amount of time. For example, you drive through it, you hear something, boom, then like after 3 seconds, boom, then after 3 seconds, boom. Usually, it's very interesting because those are caused by the cracks in the pavement, and they occurs over a certain distance. And usually the distance is very interesting. The distance is like, for example, 10 meters, 5 meters, and they're pretty even. They're equal. They're not exactly the same thing, but they're close. So those are caused by thermal cracking. Because when we construct the pavement, we would do it in summer, so that at relatively high temperatures, right? However, when we move from summer to winter, we have cold temperatures, so that will make the pavement shrink. And make it shrink if we don't make a cut. If they're continuous, what's going to happen is that they're going to pool. For example, you can imagine that yourself as a point inside the pavement. What's going to happen is that you need to shrink. You need to pool your neighbors, and everybody try to pool the neighbors. What's going to happen is that we're going to have tensile stress, right, developed in the pavement. Yeah. And when that tensile stress exceeds the strength of the material, we're going to have cracks developing in the pavement. And that's why when you go from like 10 meters or to 15 meters, you will see a crack. So that crack is called longitudinal crack, right? It's also called a cold temperature crack. This is the example. So now I'm showing you guys how to analyze that type of problem using very simple multiphysics. First, let's take a look at the relationship between stress and temperature. Take a look at the coupling between stress and temperature. Actually, there are two types of coupling. When we are talking about a coupling, we have two fields. You need to think about it this way. The coupling can happen along any direction. So you have two objects. When we are talking about a direction, we have at least two directions, right? Move from one to the other, and move from the other back to the first one, right? So there are two directions. So coupling can be the same thing. You can have two directions. So for example, if one thing changes, it can cause some changes in another one. And if the other one, changes due to some reason, that change will also result in some actual changes to the first one. So we have the same thing, when we have both heat transfer and a thermal field. But in most cases for thermomechanics, we only talk about one-way coupling. That's the coupling from thermal field to the mechanical field, such as thermal stress. If we have something, we have temperature change in that thing, that will make it shrink or expand. That will cause stress. So that's one way of coupling. But this coupling could be two-way. For example, if we have stress and strain, we have deformation. For example, that's an example is like this. You have something like this. I have this chair. I try to deform the chair, something like this. I'm doing this like over like 10 days. What's going to happen? Even my hand. Let's assume that my hand has the same temperature as this one. What's going to happen is that this stress and strain will cause something called strain energy. So I convert the energy from my hand by doing something. I do work to this chair, and that work will eventually be transformed into a thermal energy, and that will increase the temperature of the chair. Right? This is the coupling from mechanical field to thermal field. But this coupling exists. However, it's not that as significant as the coupling from the thermal field to the mechanical field. So usually when we talk about thermomechanics, some people overlook that part. So here we will do it in the same thing. We will emphasize the coupling from thermal field to the mechanical field. But I want to let you guys know that the comprehensive consideration should have two-way couplings. So in order to do this one, let's do it in this way. So first, we start from something that's really simple. So we start from 1D. So let's say we have a rod like this, and the original length of the rod is L, and we have temperature T sub 0. So that's the initial temperature. And then what's going to happen next is that we increase this temperature from T sub 0 to a different temperature. Let's call it T. And because temperature increases, for most materials, if we increase temperature, what should we have? Expansion or expansion, right? For some very weird cases, for example, the water, when the temperature gets to like 4 degrees Celsius, they may shrink it. They may shrink. So, but let's consider the most common situation. So we can have a deformation. Let's say now it has a elongation of delta L. Some people ran experiments with this very simple stuff, and they found one thing, that is the delta L, the change in the length, is proportional to the distance between the initial and the final temperature. So if you run the experiments, you can find the same thing. So to find that delta L, actually a more comprehensive description is that delta L over L. Delta L over L is like a stream, right? So stream, here I use this sign, means proportional to T minus T sub 0. Then, if they try this, with the same material, they will find that, the proportionality between this one and this one is a constant. So that's a material property. If you use a rod made of a different material, you will find that it's also proportional. However, you have a different proportionality. So that means you have a different material constant. Then people say that, we have this. Then let's propose a new parameter to represent this proportionality. So they said that delta L over L now is alpha L times T minus T 0. And some people say that, okay, for this T minus T 0 is a change in temperature. So let's use the sign delta T. So it's a little bit confusing because in the past, we used a triangle like this to represent Laplacian, right? Now it's not Laplacian, so don't be confused. This just means change something. It's a change at a macroscopic scale. So this is not Laplacian. And alpha L, so it's a material property. So alpha L, it has a name. It's called linear expansion. Thermal expansion coefficient. So now you know the meaning of this L. L means linear. So L, this is what the L stands for. So L, so this is L, alpha L. And linear usually means 1D. And if it's 2D, we usually call it surface. So when we talk about, for example, one sheet of paper, we want to talk about its expansion along 2D direction. So usually we use alpha S. That means the surface thermal expansion coefficient. If it's 3D, we use alpha V. That's the volumetric thermal expansion coefficient. And I'm going to introduce what's the relationship between them. Before that, here I want to keep moving on, because if you take a look, you can see that this delta L over L, this is kind of very primitive definition for stream, right? This is kind of very primitive for stream. And we know that if the material is elastic, we're going to have the stress will be proportional to stream, right? So in elastic material, actually simple linear elastic material, so we have the stress is proportional to stream, and the proportionality between them is the constitutive relationship, is represented by those elastic constants, Young's modulus, Lamé constants, shear modulus, all of them, right? But if it's linear elastic, usually we just need two of them. And the other, if we give two of them, the others can be derived using the given two parameters. Based on this, we can get one thing, that is sigma should be proportional to this delta T as well, right? This is straightforward. And if we are talking about 1D, so in 1D, we can get this. Sigma equals E alpha L delta T. So E is Young's modulus. As I mentioned, Young's modulus is defined as the proportionality between the elongation, the change in the length, with and over the change in stress. So that's the definition of it. But this is not complete, because if we take a look, for stress, usually we say that which one is positive, is compressive, or is tensile. Which stress is positive? Tensile, right? In solid mechanics, it's compressive is positive, but in other mechanics, types of mechanics, usually it's tensile is the positive. However, if we say that we have something like this, and if I fix the two ends of it, and then I put it on a fire, what's going to happen? What type of stress we should have? I fix two ends of it, I put it on a fire, compressive or tensile? You constrain the two ends of it, you don't let it deform, and put it on a fire. Compressive, right? So what is compressive? Is positive, negative? Negative, right? Yeah, right? Yeah. And if you put it on a fire, that means the temperature change is an increase or decrease? Increase. And in most cases, we say the increase is positive, right? So increase is positive, and here stress is negative because it's compressive, right? So this E is the positive constant, and alpha L is a material property, so it's positive. So that means we should have a negative sign in front of it, right? So we need to add a negative sign in front of it, because when you fixed one thing and then put it on the fire, the temperature increase, you're going to have a compressive stress. So if you cannot understand it, go back to the example that I just given. You have something, you constrain it, you don't allow it to deform. You put it on fire. Then you will increase the temperature, right? You get a positive delta T. However, you get compressive stress in that condition. So you get negative stress. Positive, negative, and everything is positive, so you have a negative sign here. So this equation is valid for 1D case. And when we move to 1D to 3D, so if we move from 1D to 3D, for 3D we have the same thing. That now in that case it's not a change in length, it's a change in volume over the original volume. And this one is proportional to T minus T0. So we can get the same thing. And eventually, we can define one variable, that alpha V. Let's do it slowly. So delta V over V. So first we define one new variable, alpha V. That's the volumetric thermal expansion coefficient times T minus T sub 0. You can see that we do it in the same way like what we did in 1D, but the only difference is now we're talking about volume, not L anymore. And because of that, we will see that alpha V is delta V over V times delta T. And one simple way to relate, this 1D alpha L with this 3D delta V is in this way. It's like, now you think about it, you have one object, a 3D object. You put it on the fire. Let's assume that the whole object has one temperature. The initial temperature of T is T0, and the final one is T. You put it on a fire, so that, for example, if it's a ball, the ball will expand along the 3 directions, right? Along one direction, we will have this delta L, delta T, something like this. And what about the change in volume? And you will see that the change in volume is the summation of all the changes along the 3 directions. And that will give us the following direction. That is, alpha V is alpha Lx, x direct alpha Ly plus alpha Lz. But if the material is isotropic, that means it has the same material property along all the directions. So that means all the alpha L should be identical. So we have 3 alpha L. So here I need isotropic. Is it clear? So just like the change of the volume along 3 directions is a summation of the changes along all the 3 directions. This is the condition. We need to have the isotropic condition so that it's 3 times of them. Otherwise, we need to use this one, the summation of x, y, and z. And with this equation, now we can, if we are talking about a 3D case, in 3D case, so here this is 1D, right? If we go to 3D, we're gonna have a relationship between stress and delta T as well, but the relationship gonna be like this. So it's sigma in 3D case. Actually, this is just the volumetric stress, not the shear stress. So equals, we still have the negative sign, and we have epsilon V, we have delta T, and this, we have a constant here, and this constant is not E anymore, it's K. K is the volumetric modulus. So this is the constant. That's the definition of K. As I mentioned, we have multiple variables. Oh, sorry. This is not epsilon V, it's alpha V. Apologize. So you can see that 1D is similar, 3D is similar to 1D. But first we have alpha V instead of alpha L, and second we have K. So what is K? K is just like, if you have a ball, if you put a compressive stress on the outer surface of the ball, you try to compress the ball, you will get a change delta V, right?
Yeah.
And the strain, that volumetric strain, is delta V over V, right? And that strain, delta V over V, should be proportional to the stress P you put on it, right?
Yeah.
That proportionality is K. So this definition of K. L is different thing. It's like you have 1D stuff, you pull it or you compress it. Delta L over L is proportional to the stress, the sigma x. So that proportionality is E, is Young's modulus. And you can see that in this case it's 1D, so there's no compressive stress along the other two directions. It's free. So when you pull something, what's going to happen is that if this is elastic, if you pull it, it's going to be thinner and thinner, right? But if you confine it, you say that, well, don't allow deformation along this YZ direction. What's going to happen is that it cannot change.
Yeah.
You don't have enough deformation. In that case, it's a different type. It's a different type of elastic constant. It's not an E anymore. So we define these different constants in different ways. So you've already seen E and V a lot, right? And now, when we are talking about get into this course, we talk about lambda and mu, right? And mu is a G that you learned in some other courses, the shear modulus. And now we have one more thing, K. And we still have some other things called M. And more than that, depending on how to define the elastic constant, what's the boundary condition that you place when you want to cause a deformation. But again, we have a lot of them. However, for any homogeneous isotropic material, only 2 of them are needed to describe the material. So the other things can be derived based on 2.
Yeah.
That's why in your lab 7, I give you E and nu, yeah. But you can get lambda and mu based on equations, right? So in later lectures, if we give you something else, you can also derive them. Yeah. If you want a relationship between K and E and mu, go to Wikipedia, search Hooke's law. You will get a table. Or you can also find a simplified version of the table also in the book. So again, this is K. So that's the meaning of K. And we get this equation. Okay, now with this equation, next step, we have the coupling. Actually, it's one-way coupling. So here I offer extra information. So if we are talking about I said there's not direction for the coupling. That's if we have a stress and strain that can cause temperature changes, right? If you cause some stress and strain over time, that stress and strain will cause the strain energy to be converted to heat thermal energy. So that will change the temperature. So what's going to happen is that, because in the heat equation, at the very beginning, I add one thing. That's something called a source or a sink, right? So, for example, if you cause stress and strain, what's going to happen is that can work as a source in this one. So it will generate heat over time due to this different stress and strain. And that source G is stress over strain. And is the change of this one, let's do it in this way, is the sigma d this. And here, the point means temporal derivative. So this is the change of strain with time. But again, it's not required in this course. I just want to offer some information because this is the definition of strain energy. So G will have a unit of the change of energy per time, so joule per second. So that's the definition of a source or hint. So we generate that amount of heat or energy, thermal energy, over a unit time. But again, we don't do this. We don't have practice for this one. Let's get to the second part for the governing equation. So for the gravity equation, when we were deriving the gravity equation for the mechanical field, which equation did we start from? So when we do that for heat transfer, because the transport problem, so we start from that transport equation, right? That equation of conservation. But for heat transfer, which equation did we start from? Newton's second law, right? And then because it's mechanical field, so it's the simplified version of the Newton's second law. It's not, the Newton's second law says F equals ma. Yeah. And if it's static, that there's no acceleration, right? So there's no change over time. So just F equals 1. So that's equilibrium equation. And if we move from the macroscopic equilibrium equation to the microscopic, we have this equation. This is also the equilibrium equation. Just remember it. This is the equilibrium equation, macroscopic. And in our case, in the previously, we only have one sigma. But now we have two of them. So one is the elastic stress. The other one is thermal stress, right? So now T sigma equals two things. One sigma E, the other one is sigma T. So E here is elastic, and T here thermal. And for the elastic stress, sorry, we need to put a bar here, so they're tensor. So elastic stress, actually we've already introduced the definition of it. It's like this. It's like this one. But however, one thing is missing, because this one, K is a constant, is a scalar. Alpha V, constant, scalar. Delta T, scalar. So this sigma here is also scalar. However, here we have, now we not deal with tensor, second order tensor. So sigma T has something like this in it. So how can we convert this one to this? What's going to happen is that we time the whole thing with a I tensor. It's the unit matrix. This is related to one thing that we introduced before. It's related to that delta ij. This is the Kronecker delta, right? So what does Kronecker delta says? They represent something like this: 1, 1, 1, 0, 0, 0. So you can see that this one is amazing because you can convert something. For example, this is 1. If this is 10, if the whole thing is 10, you multiply this one, you will get a 10, 10, 10 along diagonal, right? Yeah. And off diagonal, you have zeros. So by multiplying a scalar and a second order tensor, we get a second order tensor. So it's very common, in the later, if we're going to do fluid dynamics, you can see this again. So again, these two are the same thing. The I bar and delta ij is the same thing. This is just the vector of it. Some people, they prefer use delta bar. It's the same thing. If you add a bar to it, that means, but sometimes people use delta, some people use I. So this is unit matrix. With this one, let's see how we can derive the equation. So first, for M is a mechanical field. If we write down the full equation, we're gonna get lambda plus mu. Do you guys still remember? What should we have? Either the gradient of divergence or divergence gradient, right? This one is the gradient of divergence. It's the weird one. And the other one only have mu, and this one is the divergence of gradient. So this is Laplacian. And plus F, body force, equals 0, right? But now we should have one more stress. So if you substitute this into this as well, we need to have one more term here. And this term is minus K epsilon V. So now let's stay away from that delta anymore, because now it's confusing. So we don't use delta, we use T minus T0, okay? Let's avoid confusion. So we do that.
what's going to happen is that we will have the gradient of t minus t0. Made this mistake again. It's alpha. So the reason is that, but you can see that here. So if we combine these two, we should have this delta E plus sigma E and sigma T equals 0. And for sigma T, if you substitute this equation into here, what's going to happen is that if you have the divergence of something, anything, just make an example here, U, I, this thing, this is one of the identities that we will have in tensor analysis. This one equals the gradient of U. So that's why you can see that when we move from here to here, the I disappears. There's no I here, just due to this identity. So I is gone at this point. This point is gone as well. So we convert this one from divergence to gradient. You can prove it yourself if you're using those index notation, just like what we did before. And for this thing, the gradient of t. So let's say initially t is a constant. For example, if you're simulating an area, with a t0 is a constant, what's going to happen is that the gradient of constant is going to be 0. So in that case, you will get this one actually can be simplified into just a gradient of t. Depending on whether your t0 is a constant. If it's a constant, then you can do the simplification. This is for m. For t, we have the same thing. Rho c, this one equals lambda, that Laplacian of t. Right? And here we should have g something, but we overlook this one. Don't consider it. So for boundary condition, you do it in exactly the same way, like what you did for thermal field and the mechanic field. So there's no new things.
I think I'm falling for you.